All right, this is part 2 of pitch class set theory. So a few reminders before we dive deeper. Remember that all pitch class sets are considered equivalent, no matter whether you transpose them or invert them. Okay, we're going to see that more today. Okay, so the set class is actually represented by its prime form. Okay, so if you look at the one on the left down here for the example, we've got C, C sharp, D sharp, and E. If you knew the integers already, you would know that was 0, 1, 3, and 4, okay, which is actually also its prime form. Okay, all prime forms are going to start with a 0. Okay, now the one on the right is the same like intervallic content, right? I just transpose it up a perfect fourth or up 5 semitones. Okay, so let's say, for instance, that we had just this one on the right as our set, and we were trying to find its prime form. Okay, so if you knew the integers, then you would have thought to yourself probably that this was 5. Okay, this is a 6. This is 8. And A is 9. Okay, so that's its integer representation for that set, but it's not its name. Okay, its set class will always have to start with a 0. Okay, there are a couple of ways that you could figure it out. You could just start with this f equaling 0 and then basically just count up. Okay, so if f is 0 and f sharp is just 1 away, and then 2, 3, so G sharp is 3 away from that f. And if we went up one more, we're at number 4, so that A is 4 away from the F. Okay. You could also do math if you really love math. And we're basically just trying to get this to where the first number is 0. Okay. Okay, so what we could do is we could just subtract 5 from that first number 5, and that would give us 0. Then we just need to subtract 5 from everything else too. So 6 minus 5 is 1. 8 minus 5 is 3, and then 9 minus 5 is 4. Okay, all right, and it's actually the same if I went backwards with this too. So for instance, if I had you count from A and then we went backwards or inverted, right? A down 1 is that G sharp, 2, 3 gives us to F sharp, and then 4 gives us down to F. So it's the same 0, 1, 3, 4. So this one is like symmetrical backwards. Okay, it's the same forwards and backwards. Now you can only find the prime form if you've already figured out the normal order. Okay, so you have to get it in its smallest span in ascending order in order to be able to find its prime form. Okay, next. We're going to clear those drawings before I go to my next slide. Okay, the next thing that we're going to figure out is the interval class vector, which we will just abbreviate as ICV. Okay, that's the list of all of the interval classes contained within a pitch class set. Okay, so we're going to kind of expand on that set that I just showed you. So we're going to add in 6, which would be like F sharp. Okay, so the set now is C, C sharp, D sharp, E, and then F sharp. Okay, so we already have its prime form, so the set's name, which is 0, 1, 3, 4, 6. The interval class, notice the set was in parentheses. Interval class is going to be between like those little caret signs, okay? And what that means is that within that set, we have 2 occurrences of interval class 1, which could mean either a minor second or a major 7th, right? We have 2 occurrences of interval class 2, which could mean either a major second or a minor 7th, sorry. We have 3 occurrences of interval class 3, 1 of 4, 1 of 5, 1 of 6. Okay, and of course, remember those interval classes are considering both like the upwards and like its inversion, right? So a minor second is the same thing as a major 7, right? Same thing as a perfect 4th is the same thing as a perfect 5th if you inverted it, right? Okay, so to figure this out, we use a triangle of differences. Okay. All right, so how we figured this out, what's going on here, this first line if you think about it, it's like 6 minus 0, 4 minus 0, right? You could just have that line. Okay, so to figure out the second line, we basically go into this next number and we subtract that from all the other numbers that are larger than it. So 6 minus 1 is 5, and then 4 minus 1 is 3. 3 minus 1 is 2. Okay. Now if we keep going down, we're going to now subtract 3 from the larger numbers. So 6 minus 3 is 3. 4 minus 3 is 1. And now we're going to just subtract 4 from the larger numbers, so just 6 minus 4, which gives us a 2. Okay. All right. So next, we plug that into the interval classes. Okay. So we have 2 occurrences of the interval class 1. Okay. And then for interval class 2, right here, we had 2 of those as well. Right. We had 1, 2. For interval class 3, we had 3 of them all right there in a diagonal. Okay. Then we had only 1, 4, 1, 5, 1, 6. Okay, and then we just took all of those numbers and put them left to right between those little caret signs, and that was our interval class vector. Okay. Okay, now we're going to revisit that Vebern that we saw in the previous video. Okay, and we're going to figure out both the prime form of these sets, so like the set class name, and then we're also going to figure out their interval class vectors. Okay, so we're going to take the set 1 first, okay, which we talked about in the last video. So if you remember, the interval or the prime form of this one, we should use this one. Okay, this is the normal order. It's the smallest span of this. Okay, so we're going to use that one to figure out its prime form. Okay, so there are a couple of ways that you could figure it out. Okay, you could either start with B equaling 0 and then just count up from there. So B is 0, so C is 1, C sharp, 3 if we count up to D, okay, and then another one up, 4 for E flat. Okay. Okay, so 0, 3, 4. Okay, you could also think about it this way. You could think about it with those integers. So 11, 2, 3, and then minus 11 from everything. Okay, so 11 minus 11 is 0. Okay, but then we have a problem if we get to 2, right? We can't do 2 minus 11, right? So then we have to, if you can't minus your number, you have to add 12 to everything. So we add 12 to 2 first. So 14, and then we minus 11, which gives us 3. Okay. Same thing with 3. We'll first have to add 12 to that number, which is 15. And then we can subtract 11 from that, which gives us the 4. Okay. So which was what we came up with when we just counted up to. Okay. You can choose whichever one is easiest for you. Okay, this is not actually the set name though, because if we invert it, if we go backwards with this, then it actually gives us a smaller like sum basically. So if we went backwards or inverted it, we actually end up, let's do it this way, with 0, 1, 4. Okay, so you can just go backwards. So the prime form is not 0, 3, 4, it's actually 0, 1, 4, because that gives us the smallest sum of all of the numbers. Okay, that's how you decide whether you want the forwards number or the backwards number. Okay, you always want the smallest. So its interval class vector is actually pretty simple because I only had to do 4 minus 1 to figure this out. Okay. And then you can see we don't count the 0, right? We don't have any interval class zeros really in this vector, okay? So we have 1 interval class 1, we don't have any 2s, we have 1, 3, we have 1, 4, and then we don't have any 5s or 6s, okay? So that's our warm-up one. Okay, so now we're going to look at a slightly longer one. Okay, so this was set 3 in that Vebern example, okay? Okay, so going up, I just put in the pitch classes, starting with like the smallest integer to the side. Okay, this, however, is not normal order. Okay, you can see it's a pretty big span, right? We have a 10, so a minor 7 interval, and we have this larger gap right here. So we should actually be starting with B flat to figure out our normal order. So if we start on B flat, you'll see it's much smaller span. Okay, not hugely smaller, but anyway. Okay, So this is our normal order right here. Okay, so to figure out the set name, we could do the same thing. We could just count how many semitones were between the notes, right? So if you started on B flat, I'm going to do it down an octave. So B flat, 0, so that's 0, 1, 2 would be for C, 3, 4 for D, 5, 6 is our E, and then 7, 8. Okay. Okay, so we could think of it as 0, 2, 4, 6, 7, 8. Or if we go backwards, we come up with a different series of numbers. So if you start on F sharp is 0, then down to F is just 1, E would be 2, then 3, 4 gives us D, and then 5, 6 to C, and then 7 would be B, so B flat is 8. Okay, so if you look and you're trying to choose between like forwards or backwards, just figure out which one is smaller. So the smaller one, the smaller sum would be the one on the right. So 0, 1, 2, 4, 6, 8. Okay, so we're going to use that as our set name. And the interval class vector is off to that right. Okay, so to figure this vector out, okay, the top line is basically 0 minus everything. So we don't need to minus 0 from anything. So next one down, we minus 1 from everything. So 8 minus 1 is 7. 6 minus 1 is 5. 4 minus 1 is 3. 2 minus 1 is 1. So the next line down, we're going to subtract 2 from everything. So 8 minus 2 is 6. 6 minus 2 is 4. 4 minus 2 is 2. Now we're going to subtract 4 from everything. So 8 minus 4 is 4. 6 minus 4 is 2. Now we subtract 6 from everything. So 8 from 6, or 8 minus 6 is 2. Okay. All right, now when we figure out this vector, we this time have numbers that are larger than just 6, right? But there's only 6 spots in our interval class vector. So we're going to have to, consider basically like the inversions too, right? Which you can figure out pretty easily by just subtracting that larger number from 12. So if you don't remember, for 8, it's going to be the same as interval class 4. And the way you can figure that out is 12 minus 8, and that gives you 4. Okay. So the 7, then, if you think 12 minus 7, that's 5. So that 7 is actually going to be interval class 5. Okay. All right. So if we look through this, I see 2 1s. So we put in 2 for our 1 spot. There are 1, 2, 3, 4 2s. So 4 2s right there. There's only 1 3, which goes right there. Next for 4s, now remember that 8 was actually a 4 too. So we have 1, 2, 3, 4 4s. For 5s, remember the 7 was also considered 5, okay, because 12 minus 7. So we have 2 5s, and we have 2 6s as well, okay. Okay, now there's a helpful thing that you can use to kind of check your answer sometimes, or to just have it figure it out for you. Okay, there's a music theorist by the name of Alan Fort, and he actually classified all of the possible sets. Okay, so if you are wondering if you have the right prime form, then looking it up in his table would help you. Okay, if it doesn't exist in his table, that means you don't have the right prime form. Okay, his table also shows you other things too. So the interval class vectors, for instance, too. Okay, so there are going to be several columns. Okay, the way that these work is the column on the left is going to be, in the example that I'll show you, are trichords. So there's sets that have 3 pitches in it. Okay, but the one on the very right is going to be kind of its opposite. Okay, so it's going to have 9. Okay, so the ones from like left compared to right are going to add up to 12 all the time. Okay, okay, so the Fort name example that I gave you is 3-6. The 3 at the start means that that set has 3 pitches. Okay, so the first number is its cardinal number. Okay, 6 means it's the 6th one like down the list basically. Okay. The second to last columns are the prime forms. So the actual like 0, 1, 3, 4, or, you know, that kind of thing. Okay, so it's the prime form number of it. The third to last columns, that would be like between the little caret signs, is going to be the interval class vector. Then the central columns are going to be the degrees of transpositional and inversional symmetry, which we will talk about in a second. Okay, so here's kind of what the table could look like. Okay, so if you look at the very first one, 0, 1, 2, right, that would just all be semitones, right? And then if you look kind of over on the opposite side, so 9-1, it's basically kind of its opposite. It's its complement. Okay. Okay. Now there are things that you can use to help / cheat almost. And I'll put these on a separate place on iLearn so that you can find them. Okay. But I will show you what they look like. Okay. Okay. So if you made up a set, okay, let's say that my set has the pitches, so we're gonna do D and then F and F sharp. How about that? Okay. So it automatically figured out that its prime form is 0, 1, 4. Okay, so that's actually going like basically backwards, right? If you start on 5, go down, and 5 is 0, go backwards. You'd have 1 semitone, 2, 3. Sorry, 0, 1, 2, 3, 4. Gets just down to D. Okay. The fort name is 3-3. Okay, 3 because there were 3 different pitches in there. It's the third one down on the list. Okay. Then prime inversion was actually like the normal order, basically. Okay. Okay. So that's one of them. Let me go back. Now to this one. Okay, so the next one down is fun too because it shows you kind of descriptive names and properties of these things too. Okay, so you can see on these first ones, see the cardinal numbers off to the left-hand side. So like the 2-1, that means that there are only 2 pitches in there. Okay, so if you look further down and look off to the side, you can see like descriptions basically of what they are too, right? So like for instance, this one's major, minor triads, right? And then if you look even further down, there's more interesting things too. So I mean some tetrachord stuff, some blues pentacluster, right? Spanish pentacluster, anyway, so on, so forth. Okay, I think the most helpful one, save the best for last maybe. Go back. No. Okay. Wait for just a second. Okay, so here's the most helpful one maybe. It's the very last one. Okay. All right, so you could do the same thing. You can figure out that set calculator. Let's see. Let's go off of the one that I showed you. It was the set 6. Let's see if or 3. Let's see if I remember it from that Vebern. Remember it started on B flat, then I think it was C, right? Then it was D, E, then it went F. Oops, not that one. Sorry, C, D, and then it was E, F, F sharp, right? I think that was it. Okay. Okay, and then we submit it. Okay. Okay. Oh, just an FYI. Some theorists use T and E instead of 10 and 11. So 10 is T, E is used as 11 sometimes. Okay. Okay, so you can see on here the fort name for this one is 622. So the 6 is coming from the fact that there are 6 different pitch classes in there. And it's 22nd on the list. Okay. And then this one shows you some other things that we're going to talk about next. Okay, so if you look on the left-hand side, it gives you its complement right here. Okay, so, and then like an inversion and stuff too. Okay, let's see, you can like drop those arrows down so you can find different complements to it. Okay, our prime form was here. This was the normal order, right? So this is our interval class vector. It also tell you if it has some Z mates, but we're going to talk about that next. Okay, so now we're going to switch back. Okay, so some things that we kind of saw on that. Okay, So the first thing that you briefly just saw are Z-related sets, okay? That means that you have sets that aren't equivalent, okay? They don't have the same like set name, but they have identical interval class vectors. So that's what it means if it's Z-related. It means that they have the same interval class vector, okay, without being the same set. Invariant tones is what we're going to talk about next. Invariant means it's a common tone, okay? If you think back to musicianship 3, when we talked about like common tone modulation, right? Composers would often use that in like classical and romantic period to get between like distantly related keys, right? So similarly, some atonal composers use common tones to get like between sets. Some of them avoid them, okay? So for composers, it was important to know like how many invariant tones you would have if you were trying to decide to either use it or not use it, okay? So to figure out how many like invariant tones you have, you find it out by the summation square, okay? This is a lot of math in this one, I think. It's okay. Okay, so first, I'm just using the set 0, 1, 4, 8. Okay, so I'm putting it on the top and the left, okay? And then basically you just go right here and you go like 0 plus 0 is 0, right? And then 0 plus 1 is 1, 0 plus 4 is 4, 0 plus 8, 8, right? Then over here, we do 1 plus 0 is 1, 1 plus 1 is 2, 1 plus 4 is 5, 1 plus 8 is 9, right? So on and so forth. Okay, notice when I went here, 4 plus 8 is 12, which is the same thing as 0. Okay, so that's why there's a 0 right there, not 12. Same thing for right here, okay? Okay, so what that tells us is that if we transpose it to like the 0 degree, okay, then there will be 3 invariants, okay? If we transpose it to the 1 degree, there will be 2 invariants or 2 common tones, okay? So that's what that thing tells you, okay? Okay, next is the index vector, okay? So this is for the same one, the 0, 1, 4, 8, okay? So what we do is we take that same summation square and we just basically plug it into that like interval class thing down here, okay? So I have 3 zeros, 2 ones, 2 or 1, 2, so on and so forth, and you can see it down here, right? So we didn't have, for instance, have any 11s or 10s. That's why there's zeros in those spots. Okay. Okay, next we're going to talk about set complementarity. Okay, these are too big of words to say. Okay, so a complement is a set that's formed by all the pitch classes not in the original set. Okay. So if you took like those two sets, so if you take the original set and its complement, then you would get an aggregate. So altogether they would have all 12 pitch classes. Okay. So you can see those actually on the Fort collection. So like his table is classification. Okay. That's why he puts like the 3s and 9s together, right? Showing you basically the complements. Okay. So there's a literal complement. So for instance, if I did set 0, 1, 2, right, of like, so C, C sharp, D, so that's a trichord, right? Then the complement set that's literal would have 9 pitches and it would just be basically D sharp all the way up to B natural. It would just have all the pitches that weren't in the original set, okay? If you didn't have like the literal pitches, you could also have an abstract complement, which would basically just mean it's like those pitches, but like the set class basically of those. So it's like the intervals of those, okay? Okay, so a cool thing about hexachords, since there are 6 of them, 6 pitches in them, some hexachords are actually self-complementary, okay? So you can put the same hexachord together, but maybe transposed, and together it actually has all 12 pitches, okay? Next idea is subsets. So a subset is kind of like a subphrase, okay? So if we took the set 2, 3, 5, 6, 9, so that's not its prime form, right? That's just its integer representation. Then you could have literal subsets that would be like 2, 3, 5 or 2, 3, 6, 9. Okay, you could do 5, 6, 9, right? Any of those like integers that doesn't include like all 5 of them. Okay, it could be a subset. Okay. So a literal subset would be like what I just said, like 2, 3, 5, 6, where I took those exact pitches. Okay. But the abstract would be if I took basically like the prime form of the set. Okay, so if I took 2, 3, 5, 6, but if I figure out the prime form of that, so think either like minusing 2 from everything, or if you like count it up from pitch 2, which is D, that would give you 0, 1, 3, 4. So that's its like abstract subset. The superset is just the original set. In this case, the superset was that original of 5. Okay, symmetry is next. Okay, so transpositionally symmetrical sets, that means it can map itself onto itself if it is just transposed. Okay, so an example, augmented triads. Okay, so if you took an augmented triad of like C, E, G sharp, right, and if you transpose it up a major third, it would be the same, right? It would still be like E, G sharp / A flat, C, right? So it can map onto itself when it's transposed. Okay, there are much more examples like, for instance, a whole tone scale. Okay. All right, inversionally symmetrical sets can map itself onto itself if you invert it. Okay, so the same concept basically. Okay, so now back to the Alan Fort classification. So in his list, there's a middle column that actually tells you about the symmetry. Okay. All right, so let me go back for a second just so I can show you that middle column. Okay, so you can see in the middle, for example, trichord 3-1, there's a 1 and then a comma and then a 1. Okay, so that very first one is telling us the degree of transpositional symmetry. So it can be transposed once and map onto itself, basically. Okay, the next one tells us its inversional degree of symmetry. So we can invert it once and we can map it onto itself. So it just happens one time. Okay, we'll go back. Okay, and that's the end of part 2, which is probably a whirlwind of set theory. I think a few of those concepts at the end will be concepts that we won't necessarily have to use all the time in class, but we will revisit again. Okay, all right, that is it for part 2 and all of set theory.